Hello, everyone. Today we will be discussing the Big M method, an important technique used in operations research and linear programming, especially in solving constraint optimization problems. This method is commonly taught in engineering management courses because it helps managers make decisions that maximize profit, minimize cost, or optimize resources. What is the Big M method? The Big M method is a systematic procedure used in linear programming to handle problems involving greater than or equal to constraints, equality constraints. Situations that require artificial variables to start solving the simplex tableau. The term big M refers to a very large positive number, big enough that it heavily penalizes artificial variables so that the final solution will force them out of the basis. Why do we need the big M method? When solving linear programming problems using the simplex method, we normally need a feasible starting solution. But what happens if the constraints are greater than or equal to, the constraints are equal to, or slack variables alone cannot provide a starting solution? In these cases, we introduce artificial variables. However, we do not want artificial variables in the final answer because they are not real components of the decision problem. To ensure they are removed, we assign them a very large penalty represented by M in the objective function. Key idea behind the method. Artificial variables are inserted only to start the calculation, but the big M ensures they enter the initial basis, but they will be pushed out during computation because they are too expensive to keep due to large M penalty. So the big M method guarantees that the final solution is feasible, realistic, free of artificial variables. When to use the big M method, you use this method when the constraints contain 1 greater than or equal to constraints. These require a surplus variable, subtract slack, and an artificial variable to maintain feasibility. 2 equals constraints. These cannot produce a starting solution. 3. When simplex alone cannot start, simplex needs a basic feasible solution. Artificial variables via big M help establish it. Steps of the big M method. Step 1. Convert constraints into equation form. For example, for greater than or equal constraints, add a surplus variable and an artificial variable. For equal constraints, add an artificial variable. Step 2. Modify the objective function. Artificial variables must be penalized with plus M for minimization or M for maximization. Example for maximization, max z equals 5x1 plus 4x2 minus ma1 minus ma2. Max z equals 5x1 plus 4x2 minus ma1 minus ma2. This ensures artificial variables will not remain in the optimal solution. Step 3. Set up the initial simplex tableau, include decision variables, slack or surplus variables, artificial variables. Step 4. Apply the simplex method, perform pivot operations, choose entering variable, choose leaving variable, update rows, continue until optimality is reached. The large negative M ensures artificial variables get removed from the basis. Step 5. Interpret the final solution. When solved correctly, artificial variables must be 0. If an artificial variable is not 0, the problem has no feasible solution. Advantages of the big M method: works with complex constraints, ensures a logical and feasible starting point, can handle greater than or equal to constraints, integrates smoothly into simplex method. Limitations. Choosing M is symbolic. It must be big enough, but not infinite. Too large M may cause numerical instability, rounding errors in computation. Despite this, it remains a widely used and powerful method for linear programming. Conclusion: the big M method is an essential tool in engineering management, operations research, and optimization. It allows managers, engineers, and analysts to solve decision problems involving complex constraints, find optimal solutions even without an initial feasible starting point, ensure realistic and implementable results. Mastering this method not only strengthens your understanding of linear programming, but also enhances your ability to solve real-world engineering management problems.